Works for me. I couldn't have had a better lead-in presentation. I'm excited. Good afternoon, everyone. My name is Kristen Bobo, and I am a mechanical test engineer. I have about 6 years experience, mechanical test with a focus on high temperature and environmental effects for testing of aerospace materials. Today, I'd like to talk to you about our use of NASA's qualified metallurgical process in order to certify powder bed laser fusion, laser powder bed fusion, IN718 flight hardware for one-time use in hypersonic flight. So I'm going to go quickly through some of this. You guys have seen some of this already from my colleague, Dr. Robert Amaro, as he talked about his constitutive model. The basic question we were asked was, can IN718 by use of additive manufacture be safely employed in flight hardware? The specific conditions of our part included fatigue at elevated temperatures. This part was going to manifest with machined and as-built surface features, and we knew that that part was going to manifest stress concentration and non-defects. So the big question, more generally, was because additive manufacturing materials are typically associated with inconsistencies and homogeneities and anisotropic behavior. You guys have heard this a million times over the last few days. How do we overcome those problems? And how do we overcome these disadvantages in order to certify and meet requirements for certification in use of flight hardware? The first step you're going to need to establish is that you can consistently build material not only within a single build, but produce repeatable parts. So the things you're going to be considering are consistency as a function of build location in plane, X and Y, as a function of your build location out of plane or the build direction, your volume built, your proximity to your build surface or substrate, and your surface area to volume considerations. Once you've got all of those locked down, then you can start to say, okay, well, I did it once, but can I do it again and again? So the good news is there are a lot of people out there already thinking about these hard problems, and they're writing and standardizing, modifying methods related to AM and specifically with spaceflight hardware. So NASA spec 3717 specifically refers to laser powder bed fusion, metallurgical and metallurgical features and microscopic characterization for space hardware. There are more general ones and there are more specific ones. This one was most applicable to our case. The general way that this qualification process works is you develop a baseline, a start point. We called it -00 here. And then you review that not only internally, but with any stakeholders, so whomever your customer happens to be. And based off of that feedback, you'll modify that plan, and then you'll begin printing parts. In this case, we printed 3 qualification parts in order to qualify this material process control. From there, you assess those 3 parts and all of your witness samples, and if you feel, if you can ensure that your components have repeatable and acceptable features, you can move on. If not, you start over. That's it. So some of the process controls that you might be of interest, I wanted to just show a few here. We have 18 listed. There's between 45 and 65 listed in the standards. The important thing is that while the standards are meant to be written for broad use, you can tailor them to your specific use case. You can use as many or as few as you like. You're the one that has to qualify them. So if you can get consistent, repeatable results with fewer, then great. But I just wanted to give an example of process parameters that we use that provided consistent results. Just a little bit of information about the material we were using. We used a single lot of true form IN718, having the characteristics listed on the top there, build layer height of 40 microns. Our build platform was 12 inches by 12 inches of 304 stainless. Apologies for the imperial units. The most important thing here there's 2 notes. One is that we were able to manifest consistent microstructural characteristic size grains across not only builds, but in the different locations within our full build plate. We were consistent not only with ourselves, but it falls within literature for similar materials. The other thing of note here is our stress relief and hip procedure. The important thing is moving forward, you're going to hear me refer to as-built specimens. For our use case, as-built refers to the surface condition. All specimens, witness and otherwise, experience and go through this hip process. So that might be a little confusing for some of you who as-built need something a little different. So step one, I've been asked to do this thing. How do I even go about doing it? Step one is you print as many specimens as you can. Right here on the left, you'll see we created what we call the dog bone build. You print as many dog bones as you feasibly can, and you use those to try to qualify your intra-build consistency. The important thing, especially if you're going to claim that something you've certified is safe for flight, it might be a good idea to try to use your worst case scenarios to qualify your position. So you'll notice that moving forward, I'm going to present some room temperature and high temperature LCF. You'll notice that we define and we pick our parts from the farthest location from our optimized build area. So the methodology or the thinking being, if I can say that my worst case scenario is good enough, then my best case scenario is definitely great. So great, you built a bunch of dog bones, now prove that you can do an actual component and do it repeatably. That's the next step. So we created this dog bone build, and then we printed 3 components. They look something like this here. And from those components, we then machined out multiple specimens and perform verification and validation on those specimens to qualify our repeatability. You guys have seen this a little bit. I'm going to breeze through. Room temperature, low cycle fatigue, looks wonderful. High temperature, low cycle fatigue also looks great. But when we move into the component, we want to then begin to kind of do the same thing, but qualify our intra-build consistency. So we then move into low cycle fatigue from our component specimens, and then high temperature low cycle fatigue from our component specimens. So I've thrown a lot at you, but the main points of interest here are that we pulled multiple specimens from multiple locations, not only in our dog bone build, but across our different components. And then we did multiple conditions. So those were as built and a machined smooth surface, and then room temperature, and then 400 degrees. And the interesting thing to note is that we seem to have identified 2 distinct families of response. So the first is our machined room temperature response, which you would expect to be the baseline. This is our best, our ideal scenario. A smooth specimen at room temperature manifests with this response. The interesting thing is that even though some of these other plots here demonstrate 2 different things that you expect to have knockdowns, so as built, surface condition, or elevated temperature, you seem to get the same life debit associated with both. So that's what I'm trying to demonstrate here in terms of the 2 families. So at room temperature, you get this response, and at high temperature, you get this response, or at room temperature as built, you get the same response as the high temperature, which is interesting, but most important for our situation. It shows that we are coalescing to a single solution, to a single understanding of what happens to our material, which is important because what we're trying to say is we're consistent, right? But that's great. You did a bunch of smooth specimens. You said your part has notches in it. Okay, cool. We made a bunch of notch specimens. And so you basically take the same approach. However, because these are not specimens, these are now will be in load control regime rather than strain controlled as is typical. So once again, you go and make your specimens, you perform your tests, and you decide, oh, did I do a good job? And when your process controls are sufficient, yes, you'll get a sufficient response is our claim. So this is the results of our force-controlled notched specimens coming from the different components, both at room temperature and at elevated temperature. And just really good agreement between the two, but you don't get to see the full story until you combine everything. So we've done a bunch of testing, but what's the big story? And that is, if you take our strain-controlled, as-built, room temperature, and elevated temperature and force control data, you put it all together and you perform your 95% confidence interval, this is the data that we were able to produce, which is extremely exciting. Good repeatability, good agreement, and a good understanding of our consistent ability to produce this quality. So at this point, we get to say, yay, yes, we don't have to start over. And we move on to flight hardware. So what does that look like? Now you move into your production process. Step one is that QMP that you just validated gets locked down and does not get changed. It now becomes your master QMP, and you move on to component builds. The main thing of interest here is your printing, you're doing fine. Every 5th print gets sampled and inspected thoroughly. If you find deficiencies in that 5th print, you go back and you look at your past 4 prints. If you determine that your past 4 were fine and your 5th one just happened to be an outlier, great, your process worked. But if you find deficiencies within your past 4, you need to stop and you go back to and repeat the QMP process completely. So you define a new qualified metallurgical process, and those parameters get changed, and you now have a QMP-2, and then you can move forward. So this is just really a standardization and a codification of process parameters. So how do we do AM repeatably in the same way that someone else is somewhere else? And really, the proof of that is, can you meet what other people have done? So this is our data compared to ROT Inc. IN718. Our data is in gray and yellow at high temperature here. And then the literature is in the darker red and then in the blue, which is a pretty good agreement. But I think most importantly, we were using NASA's qualified metallurgical process, right? This is NASA's data in yellow or orangish, as built and machined on the right. If you can get that kind of agreement between 2 different AM machines, 2 different sets of people not talking to each other, I think this becomes your basis of understanding of consistent quality and consistent ability to create repeatable parts. And not only is this great in itself, but I think it's a potential really valuable path forward for leveraging the work that everyone else is doing, right? That's the downfall of AM is there's all these different knobs to turn, and everyone's doing this interesting work, but can I use your work? Usually not, because it's not the same as what I'm doing. Now we have processes that allow us to do that. And I'll wrap it up here with those conclusions that we were able to manifest homogeneous and specimens, not only in deformation and life response, but because of those qualities, we were able to get consistent fatigue life response. And the exciting news is specifications available out there already can be successfully tailored to address your potentially your more narrow defined use cases. And the implementation of those processes, practices, and methods provides a path forward for meaningful standardization and comparison of additive manufacturer material characterization efforts to really leverage the work that everyone's doing. Thank you so much for your time, and I'd love to answer questions.
Thank you, Hayden.